Hello, it's lecture 3, stat 135. Last time we did section 1.4. We talked about what it means for A and B to be independent. So A and B are independent if the conditional probability is the same as the unconditional probability. In other words, probability of A given B is the same just as the probability of A. Or equivalently, the probability of A intersection B is the probability of A times the probability of B. We then also did Bayes' rule, and we saw how to make a tree diagram. So we saw an example: a factory produces two models of phones, phone 1 and phone 2, that are good or bad. And so the first arrow is the prior. That's the probability, for example, that you have phone 2. This is not conditional on any data. The second arrow is called the likelihood. It's conditional. It's a conditional probability. So it's a probability that you're bad conditioned, for example, that you have phone 2. And Bayes' rule gives you a formula for the posterior in terms of the prior and the likelihood. So it's the prior times the likelihood divided by a constant. And so we can write that the posterior is proportional to the prior times the likelihood. Today we're going to go over student responses from the concept test and spend more time on section 1.4 and 1.5. So the concept test we had asked you, it said a deck of cards is shuffled. What's the chance that the top card is the king of spades or the bottom card is the king of spades? So the top card of being the king of spades is mutually exclusive to the bottom card being a king of spades. And one student said it was B because if the first card isn't correct and you draw a second card from the remaining pool of cards, then the chance of drawing the correct card is 1/51. Well, this actually doesn't apply to the addition rule, which is what we want to apply here, because the condition rule involves unconditional probabilities. And when you write 1/51, you're clearly conditioning on something. Another student incorrectly said that with replacement, B is correct. So in fact, with or without replacement, D is correct, because here we're just picking one card. It's either the top card or it's the bottom card, since that's what A and B are. We're not picking more than one card, so it doesn't matter whether you're drawing with or without replacement. Another student didn't have a neighbor. Oh, boo-hoo. So next time, sit next to somebody. And the correct answer would be D, since they're both the same cards and can't happen at the same time. It should be 1/52 plus 1/52. So we spent a bit of time looking at variations of mutually exclusive and independent events. So just remember that red cards are hearts and diamonds, black cards are clubs and spades. We say that two events are dependent if the conditional probability is not the same as the unconditional probability, and is mutually exclusive if the probability of the intersection is 0. So for example, draw a card from a deck and let A be the card is red and B the card is a heart. Well, since a heart is a red card, the probability of A conditioned on B is just 1. Which is not the same as just the probability of a red card. So this is dependent, and I then had you fill out this table here. And so, for example, if A is red and B is heart, then those are mutually exclusive because you can't have. Those are not mutually exclusive because you can have a red heart. However, as we just said, it is dependent. If you have a red ace, that's also not mutually exclusive because you can have a red ace. It is dependent. It's not dependent because if you know that you have an ace, that doesn't give you any information about whether it's red or not. if you have if A is red and B is spade, those are mutually exclusive because you can't have a red spade. And it's also dependent because if you know that you have a spade, then it can't be red. So there's a dependency between red and spade. And the last one's kind of a curious one. If A is that the card is green and B is that it's an ace, well, clearly those are mutually exclusive because you can't have a green ace. And furthermore, they're dependent because knowing that the card is an ace, knowing the card is an ace doesn't tell you anything about whether it's green or not. Or another way to say that is that the probability that it's green is empty, independent of whether it's an ace or not, because there's no such thing as a green card. I should note here that the conditional probability, the probability that it's ace given green, does not exist, since you can't condition on the empty set. The only way you can get A and B to be mutually exclusive and independent simultaneously is for A or B to be impossible, and that's the situation in the fourth row here. So we then did a concept test. Suppose A and B are two events. Probability of A is 0.5, probability of A union B is 0.8. Is it possible for A and B to be both mutually exclusive and independent? So the answer is no. So if it's mutually exclusive, that means that the probability of A union B would be 0.5 plus the probability of B. So probability of B must be 0.3. And then probability of A intersection B being mutually exclusive is 0, but that can't be 0.5 times 0.3, so you can't have independence. Now, if you make the union 0.8 and probability of A being 0.8, then it is possible for A and B to be simultaneously mutually exclusive and independent, since in this case probability of B is 0. And so, as I said, the only way that you can have mutually exclusive and independent is when one of the probabilities is 0. So then we moved on to section 1.5, and here's a problem invoking trees and Bayes' rule. So we have a prior here, the probability of having a disease, and we have likelihoods, the probability of testing positive given the disease or testing negative given that you don't have the disease. So if one person's picked at random from the population, given the test is positive, what's the chance he has the disease? So that is a posterior. And so we can make the tree as sort of an intermediate step and find the probability that we test positive and then the posterior. So I've drawn the tree here, and the two branches give you the probability of testing positive. So that's a sum of these two branches in the multiplication rule. So we have 0.0543 there. And then the posterior is proportional to the prior times the likelihood, which is the top branch divided by this constant 0.0543. So here's another example where we have this funny shaped die. So the die lying flat is 1 or 6 on the top, and it's a fair die when t is 1, so it lands flat 1/3 in that case. So we're told here that we have a box, it contains 3 shaped dies, D1, D2, D3, with probabilities 1/3, 1/2, and 2/3 respectively of landing flat. One of the 3 shapes will be drawn at random and rolled. What's the chance that the number rolled is 6? Can you make a tree? So we So we randomly choose a die, so that's the first arrow, and then given a die, we know what the chances of getting a 6. So for example, if we have D1, the chance of getting a 6 is half of a third, and the chance of not getting a 6 is then the complement of that 1 minus 1/6. If we have D2, the chance of getting a 6 is half of a half, or 1/4, and the chance of not getting a 6 is 3/4, and so on. So we can calculate the probability of rolling a 6. It is the probability of rolling a 6 is the sum of rolling a 6 having die 1, die 2, or die 3. And these are mutually exclusive, so we add them up. And we can find everything here, and we get 0.25. So finally we were asked to find the posterior, and the posterior is given by Bayes' rule. So we have the prior times the likelihood divided by this constant that we computed above. So all the problems are of this nature, and you'll get used to it pretty quickly. Next time we'll start and finish quickly 1.6 and on to chapter 2. Have a great day. See you Wednesday.